Welcome to Jeremy's IT Lab. This is a complete course for the CCNP ENCOR Enterprise Core exam. In this video, we will review Layer 3 forwarding, specifically route selection, which is a very important concept to understand. I already have the lab notes open here, but let me outline this lab. First up, each subnet is 192.168.xx.0/24. And the XX is the router number or numbers. For example, the segment between R1 and R2 is 192.168.12.0/24. The segment between R2 and R5 is 192.168.25.0/24, etc. You'll often find addressing schemes like this used in labs to make the lab simpler to understand. If there is no logic to the addressing scheme in a lab, it just becomes unnecessarily confusing. Similarly, the IP addresses of the routers follow a scheme of .x, where the router number is used as the final octet of the IP address. For example, all of R1's IP addresses end in .1, all of R2's IP addresses end in .2, etc. So, what are we actually going to do in this lab? We will examine R1's routing table and determine which routes will be used to forward packets that PC1 sends. By the way, I am using the CML desktop node for PC1, which is an Alpine Linux node that also includes a GUI if you prefer to use that instead of the CLI. I'll be using the CLI in this video though, since I'll just be using the PC to do traceroute. Now, what addresses will we traceroute from PC1? They're all listed in the lab instructions. Actually, these are all IP addresses configured on loopback interfaces on R5. Let me access the CLI of R5 to show you that. Enable Show IP Interface Brief. So here are the 5 loopback interfaces with the IP addresses we will traceroute from PC1. Now, PC1's default gateway is R1, and R1 has 3 possible paths it can use to reach R5. Via R2, via R3, or via R4. R1 is learning routes from these 3 routers via 3 different routing protocols. So for each of these 5 destinations, we will determine which route R1 will select to forward the packets. Now I'll return to the lab notes. Step 1 of the lab is to examine the routing table of R1 and determine what routing protocols R1 is running. So I'll access the CLI of R1. Enable. Actually, before viewing the routing table, an easy way to see which routing protocols are running is Show IP Protocols. At the top of this output, it says Routing Protocol is Application. You can ignore this output. I believe it is related to SDN, but that is another topic. Next, Routing Protocol is OSPF1. So, OSPF is running with a process ID of 1. Note that it is enabled on interfaces G00 and G02, which is connected to R3, so it seems R1 is using OSPF to learn routes from R3. Below OSPF, it says Routing Protocol is EIGRP1. So EIGRP is running with AS number 1. Toward the bottom of the EIGRP section, it says Routing for Networks 192.168.1.0, which is the G00 interface connected to PC1, and 192.168.14.0, which is the G03 interface connected to R4. Remember the addressing scheme I explained earlier. So, R1 is using EIGRP to exchange routing information with R4. Finally, at the bottom, we have RIP, and it says Routing for Networks 192.168.1.0, the LAN interface, and 192.168.12.0, which is G01 subnet, connected to R2. So R1 is using RIP to learn routes from R2. Now let's actually check the routing table. Show IP route. So R1 has quite a few routes here. For the purpose of this exercise, we don't need to see the connected and local routes. So let's filter the output to only show EIGRP, OSPF, and RIP routes. Show IP route, pipe, and then exclude. Now what should I exclude? The exclude keyword instructs the device to not display any lines that include whatever keyword you specify. I want to instruct the router to exclude the lines that say directly connected. I'll use the keyword directly to filter these connected and local routes. Okay, the output looks a bit nicer now. But I'd also like to remove these lines that say X is variably subnetted. These aren't routes, they just indicate that we have routes to subnets of classful networks, and the routes have various prefix lengths. For example, at the bottom it says 203.0.113.0/24 is variably subnetted. 3 subnets, 3 masks. Well, 203.0.113.0/24 is a classful network, a /24 class C network. But we have 3 routes below to 3 different subnets with 3 different masks, /27, /28, and /29. Note that the 203.0.113.0/24 is variably subnetted statement isn't a route. R1 doesn't have a route to /24. So we don't need this output. I will go back to my previous command, add another pipe, and also exclude all lines that include the word variably. Okay, we have reduced the output quite a bit. Note that there are still a few places where it says X is subnetted. For example, up top it says 4.0.0.0/30 is subnetted 1 subnets. That means we have 1 subnet of a classful network. 4.0.0.0 is a class A address, so by classful rules, its prefix length should be /8. However, the route here is /30, so this output says it is subnetted. It doesn't say variably subnetted because there is only 1 prefix length, /30. In the variably subnetted example I showed before, there were subnets of various prefix lengths, /27, /28, and /29, as you can see in this screenshot. Note that we shouldn't filter these X is subnetted lines from the output. If I filtered these lines, we wouldn't know the prefix length of these routes. For example, we have a route to 4.8.8.8, but this line doesn't say the prefix length of the route. It only says 4.8.8.8. We have to look at the line above where it says /30 to know the prefix length. However, keep in mind that this 4.0.0.0/30 is subnetted line isn't a route. R1 has a route to 4.8.8.8/30, not 4.0.0.0/30. And if there were multiple subnets with the same /30 prefix length that fit in the 4.0.0.0 classful network, they would also be displayed here. Here's an example. 4.0.0.0/30 is subnetted 4 subnets. In this example, the router has routes to 4.0.0.4/30, 4.0.0.8/30, 4.0.0.12/30, and 4.8.8.8/30. But once again, keep in mind, it doesn't have a route to 4.0.0.0/30. This is just a peculiarity of how routes are displayed in Cisco iOS. I will review how to read the routing table again later in the course, when we cover static and dynamic routing. But I never explained these X is subnetted or X is variably subnetted lines in the CCNA course, so I wanted to briefly mention them here. So that's enough explanation about how to read the routing table. Let's actually check the answers to the lab. Referring back to the lab notes, the first destination is 203.0.113.113. If PC1 pings that address, which route will the ping take? Take a look at the routes here in R1's routing table. It's definitely one of these 3 routes at the bottom. 203.0.113.96/27 via RIP, .96/28 via EIGRP, or .104/29 via OSPF. Remember, the AD and metric are irrelevant information. We are only looking for the most specific match. AD and metric were relevant when the router was deciding which routes to include in the routing table. But now that the routing table has already been made, it only cares about finding the most specific match. So let me pull up this document I've prepared beforehand. Up top is the destination, 203.0.103.113, then below the 3 routes that seem like they might match the destination. I've highlighted the prefix in blue according to the prefix length of the route. So for example, in the /27 route, the first 27 bits must match the destination. And if you compare them, they do. Now, these 5 red bits after don't match the destination, but that's fine. It's a /27 route, so only the first 27 bits have to match. Now, this first route is a match, but the other 2 routes have longer prefix lengths. So, if they match, it means they will be preferred over the /27. However, as you can see, they do not match. In the /28 route, this 28th bit is a 0, but in the destination, it's a 1, so it's not a valid route for this destination address. And for the /29 route, the 28th and 29th bits are 0 and 1, again not matching the destination. So this /29 is also not a matching route. It's not a valid route for the destination address 203.0.113.113. Therefore, the most specific match is the route to 203.0.113.96/27. Now I'll put this document aside, and let's look at the routing table again to find the next hop for that route. It's a RIP route, and it says via 192.168.12.2 gigabit Ethernet 01. So the next hop is R2. How can we confirm that this answer is correct? Go back to the lab notes, and in step 3, it says verify each of your answers using both of the following methods. Verify using a command on PC1, and verify using a show command on R1. First, let's confirm on PC1. I'll access the CLI of PC1, and then log in with username Cisco and password Cisco. How can we confirm the path traffic takes from PC1 to R5? We can use traceroute. So let's try it. Traceroute 203.0.113.113. Traceroute is similar to ping, except it asks for a response from every router in the path to the destination. So if our answer is correct, we should see a reply from R1, from R2, since that is the next hop according to R1's routing table, and finally a reply from R5. And as you can see, that is what happened. 192.168.1.1 is R1, 192.168.12.2 is R2, and 192.168.25.5 is R5's interface connected to R2. Don't be confused by the fact that this final destination, in the traceroute, is different than the address we sent the traceroute to, 203.0.113.113. Both are IP addresses configured on R5. Okay, so we confirmed the answer by using a command on PC1. Now, how can we confirm with a command on R1? Let's return to the CLI of R1. And to confirm, we can use a command you already know in a way you might not know yet. That command is show IP route, and then we can simply enter the destination IP address, 203.0.113.113. And now, it will display the routing table entry that R1 will select to forward traffic destined for that address. And as you can see, it is the /27 route. This is a very handy way to confirm which route a router will select when forwarding traffic to a specific destination. Now let's return to the lab notes. We went through the answer for that first destination step by step, but let's go through the others a little more quickly. The second destination is 8.8.8.8. Which route will R1 select for that destination? Let's check the routing table again. You can use the up arrow to return to the previous show command. So, which of these routes is the most specific match for 8.8.8.8? I'll return to my document to show you. It's not a very specific match, but it's actually the most specific match in the routing table. It's 0.0.0.0/4. /4 means only the first 4 bits have to match, and they do, 0000. So, what is the next hop of this route? Let's check the routing table of R1 again. And as you can see, the next hop is 192.168.13.3, gigabit Ethernet 02. That's R3. Since I'm on R1 already, I'll confirm that answer here first. The command is show IP route 8.8.8.8. And indeed, that is correct. It will select the route to o.o.o.o/4 to forward packets 4, 8.8.8.8. Now let's confirm again on PC1 with a trace route. I will use the command traceroute 8.8.8.8 and skip the video forward a bit since this can take about 15 seconds sometimes. Okay, as expected, the packet went to R1, then to R3 at 192.168.13.3, and then to the destination R5. This time, we are getting a reply from the interface connected to R3, IP address 192.168.35.5. Now let's go back to the lab notes and check the third destination, which is 172.20.20.27. So, which route will R1 select for this destination? Once again, I'll check the routing table of R1. There are a few routes which seem like they could match the destination. 172.0.0.0/8 and /9, as well as 172.16.0.0/24. Let's check the document again for the answer. By the way, I hope you have already figured these out yourself beforehand. This is an important skill to practice. So the most specific match is this one, to 172.0.0.0/9. The first 9 bits match, as required by the /9 prefix length. So let's go back to R1's routing table, and what is the next hop of that route? It says via 192.168.13.3, gigabit Ethernet 02. So once again, the next hop should be R3. Let's confirm that answer on R1 first. Show IP route 172.20.20.27. And yes, it did select the 172.0.0.0/9 route as the most specific match. And for the second check, I'll go back on PC1 and try a trace route to the destination. Trace route 172.20.20.27. As expected, the packet goes via R1 and R3 before reaching the destination R5. Now let's return to the lab notes and check the fourth destination, which is 198.0.27.56. And let's do the same process again. First, I'll return to R1 and check the routing table once again. Once again, in R1's routing table, there are 3 routes which seem like possible matches for the destination. 198.0.0.0/19, 198.0.20.0/22, and 24.0/21. I've already calculated the answer, so let's return to that document. And as you can see, the most specific match is the route for 198.0.24.0/21. The first 21 bits match, making it the most specific match. So what's the next hop? Once again, return to R1's routing table. And the next hop is 192.168.14.4, gigabit Ethernet 03. So the next hop is R4 this time. I'll confirm that here on R1 first. Show IP route 198.0.27.56. And as expected, the selected entry is 198.0.24.0/21. I'll check this one on PC1 too. So let's return to PC1 and try a trace route. Trace route 198.0.27.56. As expected, the packets went from R1 to R4 and then to R5, getting a reply from the interface connected to R4, 192.168.45.5. Now there is just one more destination to check. I'll refer back to the lab notes, and the final destination is 192.168.255.238. Let's go through that same process once more. First, I'll check R1's routing table to find routes that might match. Once again, there are 3 routes that seem like possible answers. We have a RIP route to 192.168.127.0/25, an EIGRP route to 192.168.255.232/29, and an OSPF route to 192.168.255.232/30. I'll open up that document one last time, and the most specific matching route is 192.168.255.232/29, the first 29 bits matching. There was also a route to .232/30, but the 30th bit doesn't match the destination, so that is not a valid route. Okay, and finally, let's confirm this answer, and then wrap up this lab. Once again, I'll confirm from R1 first, with the command show IP route 192.168.255.238. Indeed, as we just saw, the most specific route is the one to 192.168.255.232/29. The next hop for this route is 192.168.14.4, gigabit Ethernet 0/3. So that is R4 once again. For the final confirmation, I'll return to PC1 and try that trace route. Trace route 192.168.255.238. This time I'll just talk over the trace route while we wait. In this lab, we practiced a very important skill, reading the routing table and finding the most specific matching route. For your understanding, it's very important that you can do it yourself by writing out the binary as I did in this video. But also remember these two confirmation methods I showed you. One is by using traceroute to see which path the packets take to the destination. And by the way, the packets for this final destination went via R4 as expected. Traceroute tells you the path the packets took, although it doesn't actually identify the specific route in the router's routing table that was used. To find the most specific match in the routing table for a certain destination, you can use the command show IP route followed by the destination IP address. Both of these are very useful commands that you definitely should add to your toolkit. Okay, that's all for this video. I hope you learned something new. Before finishing this video, let me thank my JCNP level channel members. To become a member, please click the Join button under the video. Thanks to Jonathan Makara, Boson Software, Velva Jacom, George Streeter, Funny Dart, Nasir Chowdhury, Gustavo B.R., Gerard Baker, Marcel Lord, Pavel M., Mr. Erlison, Dragos Hirnea, Zakib Shah, Meir Salman, Mason Anderson, Vitaus194, Gina Lindley, Nehemia, Bold1C1U, Mark Jackson, Michael Carroll, Gerald Guillaume, Gabriel Braga, Renan Marias, Hector Hernandez, Ali Polat, Mara Tuba, R. Nelson, Roji Kuriakos, Roscoe Roy Gamer YT, Owad, Arpad Conivez, 5 Feet, Daniel Brown, Emiliano Correa, Leonardo Souza, Tricky Mickey 123456, Scott Thompson, Jose Alvarez, Kevin Hayes, ES, William Rosario, Hussein Yavuz, Samuel Tavares, Mustafa Irsoy, and Dear Diso. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So, if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.